Hello everyone, thanks for taking time to look into our work, HAR-GCNN, in which we present a deep graph CNN for human activity recognition from highly unlabeled mobile sensor data. This work was done at the University of Texas at Austin. It presented at the Context and Activity Modeling and Recognition Workshop, which is under IEEE Program Conference. I'm Abdullah Muhammad. I am your presenter today. I'm a PhD candidate at the University of Texas at Austin. And we start our paper. The motivation for our work that the ground truth annotation for HR is a difficult task. For example, sometimes you might ask user to annotate what he done as an activity. He might be doing some couple of activities in parallel. He might not have enough time to do this kind of labeling task. He might do this labeling later on the day. So it's very difficult to get an accurate activities labels, and it's full of errors. And this was our main motivation for developing our method. We hypothesized that humans follow a chronological order of activities. For example, on a daily basis, you might be waking up in the morning, then you take a shower, then you eat a breakfast. And you might be doing this on a daily basis actually. And for example, as a habit, you might be eating your lunch while watching a TV or typing on your phone. And this kind of activities you do on a daily basis. And it's kind of embedded into your routine and into your nature as a behavior. So we hypothesize that we can use this kind of correlation between activities to identify all the activities. And our main focus is, if we have at least one known activity in your day, can we know all the earlier activities and the next activity that you might do by knowing this one thing? So in our paper, we hypothesize this hypothesis and we show that actually it's true and it exists, and we can use it to identify your activities. So one might be wondering why exactly we used graph representation in our work. So if we have activities that are ordered in a chronological order, so they have a time representation, for example, this gray activity and this pink one. So the straightforward deep learning mechanism to be used in such a context is RNNs. The issue with RNNs, as in some literature, that RNNs accumulate errors through prediction. So for example, if it predicted that this first activity is something like eating or drinking, with an error, this error will be carried on to the next labeling activity and so on. So basically RNNs tend to diverge over long time. So as a solution for this problem, some other works and one of our earlier works, we used CNNs to model this kind of temporal things. So in CNNs, you can just simply do a kernel function over all the activities and predict their label directly without carrying on the errors between the activities, because CNN is just like a kernel function that passes through all the labels or through all the data. So there is no this kind of recurrent behavior that exists in RNNs. The issue with CNNs that they don't emphasize on the relationship between the temporal activities. For example, like it treats drinking and walking the same as it treats eating and running, and so on. So basically there is no this relationship, and this is why we have the direction of using graph CNNs. In graph CNNs, we can represent each activity as a node, and we can represent the relationship between these activities at a graph edge. And this kind of context or this kind of representation is really helpful in modeling both the activities as a single entity and the relationship between them using the graph edges. The main contribution of our work as follows. First, we introduce a new HAR problem in which the problem is formatted as using the chronological context of activities to detect unknown labels or unknown activities. Also, we propose a novel training mechanism that generalizes the models. This training mechanism is suitable to be used on datasets with no labels. It mimics the idea of the existence of unknown activities. and also generalize the sensor measurements. Also, we use an extensive set of experiments and comparison with fair baselines to compare our performance. Overall, if we take a look into our model or our approach, we have this missing activity graph. So basically we have a graph of some kind of activities and measurements, and we have known ones and unknown ones, and then we use HAR-GCNN to process this graph. So once we process it, or once we use it, we are able to predict the unknown ones, as we can see the green nodes here, which was previously unknown in the orange ones. For more of technical problem formulation, the problem is as follows. We have a measurement of sensors, and we call it F across a time. And then we have a classes or labels for these activities. We call it C across time. And then we have this pairs of measured sensors and its corresponding class label. And what we do that we have this kind of input to our model. So basically activity that happens at specific time step and activity that happens in later on in the future. And we have some missing ones like this CT+1 or CT+M. And our goal is to identify the label of these activities using all of this information. We use two datasets in our paper. The first one is extrasensory and the second one is BAMAP dataset. And there's something specific about this dataset that actually strengthens our approach or strengthens our hypothesis of chronological order. So the extrasensory dataset was collected in the wild. There was no script asked for the user to do. They just did what they do usually in their day, and then they labeled these activities. But on the other hand, the BMAP dataset or the BAMAP dataset actually was a scripted dataset. So basically they asked the user to eat, drink, run, something like this. So what we can see that the chronological order in the BAMAP dataset is actually a scripted thing. So it's a bias or systematic bias in the test. And once we go to the experiments, we will notice this effect. On the other hand, the extrasensory, because it's recorded in the wild, we actually was able to tell the true chronological correlation between the activities and use them. There's other differences between both of that. The extrasensory is a multi-label dataset. On the other hand, the BAMAP dataset is a single label dataset. The extrasensory comes with a lot of features, but the BAMAP dataset is limited in terms of the 3 sensors and the heart rate sensor. For training and testing, we use 2-to-1 split between the training dataset and the testing dataset to report our results. Here we try to construct our graph. So the graph is the input to our model. So the graph consists of vertices and edges. So each vertex, as we talked before, will contain 2 information. The first one is the features, the measured feature of the measurement. We didn't focus exactly on processing each measurement. We just used the raw measurements, and then on the other hand, the label corresponding to those measurements. And the edges, we set the edges to 1 to represent an equal relationship between all the nodes. It might be in a future work that we have a better edge representation, but for now, for simplicity, we use this kind of representation. So, and for missed activities, we want their class label to be 0. After formulating our input graph, as we described before, we use a graph CNN to process this graph. So the graph CNN receives actually 2 inputs. The first one is the vertices, which contains the measurement of the sensors and the corresponding label, which is either is known or unknown. And also to receive the adjacency matrix, which is a representation of the edges of the graph. And we use a normalized version of the adjacency matrix. This normalized version actually is a Laplacian equivalent of the adjacency matrix. And we can see that there is an etc term here where we use an identity matrix. And this identity matrix here, it emphasizes on the values of the node itself to be considered within the kernel function of the graph CNN. And the Laplacian formulation of the adjacency matrix like gives a weight for the all values of the edges or all values of the nodes that sums to a unity. So basically we don't have an explosion in our gradients. So the graph CNN acts exactly as a CNN, but the main thing or the main difference that it weights the value or the contribution between the edges by using the adjacency matrix. And this is the main difference between the graph CNN and CNN, and this is basically why our method is much better than the prior ones. Afterwards, we use a sequence of CNNs to process the embedding coming from the graph CNN. So one reason for not using graph CNN all the way long, that actually what we care about eventually is the label of the classes. We don't care about the edges anymore. The second thing that there is a known issue in graph CNNs that when you go deeper with it, they're kind of performance degrading. So basically we use CNNs here as a replacement for the graph CNN to construct our whole model. For the baseline, because our formulation did not exist before, we made up two baselines. The first one is a CNN baseline. Basically, it receives the graph itself, the vertices, but without the information of the adjacency matrix. So it has a depth that is similar to our model, and it shares the same weight or the same number of parameter, and it was trained in the same way as our model. And the labels here, K is corresponding for the kernel, F corresponding for the features, and B is for the padding. And we use this same baseline to compare our model. On the other hand, we use an LSTM baseline with the same structure, like there is an LSTM unit and then there is a head that actually processes this value coming from the LSTM to have the representation that matches our output. And all of our baseline have the same depths, have the same number of parameters, and we're trained with the same training mechanism to make sure that we have a fair comparison mechanism. The training mechanism is a contribution of our paper. We use this training mechanism to have our model generalize better, and also actually we did not have a dataset with unknown labels, right? We have a dataset with known labels, so basically we needed to enforce the existence of unknown labels. So what we did in our training mechanism that we have this graph with the features, the classes, and the adjacency, and randomly we might hide a class or two, but we don't hide like all of them. We just, at least we keep one of them known, or we add noise to the measurement. So the hiding is what actually mimics the idea or the concept of missing activities, but the noise actually helps to generalize a little bit our model and sensor. So basically it gives a wide range of measurements. And then we use this randomly hide or added noise thing as an augmentation for the original dataset, and we either train our model HAR-GCNN or our baseline models, which we described before, and then we use the loss function that could be a cross entropy in case of the PAMAP dataset, or it can be just binary cross entropy in case of the multi-label problem of the extrasensory dataset. Coming to the results, we have this table here that first we have the number of activities, second the percentage of the missing labels. All the results here are reported on the test dataset, and the results are the F1 score over the accuracy, and actually we use accuracy to see exactly how accurate we are, but it's not really representative. This is why we relied on the F1 score. And then we have the extrasensory dataset and the PAMAP dataset. So as a general notice, the performance of HAR-GCNN is actually much better than the baselines of the CNN and the LSTM corresponding ones. The second note is that we know that the CNN actually performs better than LSTM, and this is basically our assumption at the first of the paper, or our observation that RNN-based models tend to diverge over time when we have this number of activities, or actually like what we said before, that they accumulate errors through predictions. And we can see that the CN has a better performance, but still not as good as the GCN because it's missing this correlation between the nodes itself. It misses this adjacency matrix that represent the relationship between the nodes. So we can see that the performance on under 33% or 66%, it's much better, still the same thing. And there is a general notice here that the extrasensory dataset have this normal behavior of accuracy, like the F1 score, you see it. But on the other hand, when we go to the BAMAP dataset, we notice that we almost have a perfect F1 score. And we also have a perfect accuracy. And this happens everywhere in the BAMAP dataset. And if we thought about this, there is a main difference between the extrasensory dataset and the BAMAP dataset. The extrasensory dataset was actually collected in the wild. There was no script for the users to follow in doing their activities or executing the activities. But on the other hand, the BAMAP dataset, users were asked to do a script of activities. And what happens here that this high accuracy, we rely to that the models actually discovered this script. So basically, the features or the measurements did not matter in this context because the script was there. So basically, the models learned the systematic bias that exists in the dataset. And this is really important because it shows that the chronological activities can be used. And once we have this bias or this static chronological thing, we have this improved result, we have this huge result, almost perfect. But on the other hand, in the extrasensory, because it was collected in the wild, we don't have such a performance. We still have some room for improvements. The second part of the results is when we have the number of activities actually increase, like 3 to 5 to 10 and even 25. So we notice the following, that our performance in HAR-GCN actually improves a little bit, but still within the same epsilon or the same delta. As we can see, like the performance is almost constant. So basically, our model is agnostic to the number of activities. So if we have like 3 activities and one known one, in the case of 66%, we can have the same accuracy. If we have 5 activities, we still have almost the same accuracy. Once we go to the 10, it is still the same, and the 25 is also the same. So basically, this is a property that our model can generalize to whatever number of activities, and there is no rely on the number of activities provided as an input. On the other hand, when we dive into the CNN or the LSTM baseline, we know that there is actually huge improvement in the accuracy. Like for example, in the case of 3 active, there is this 0.6 F1 score, and it jumped to 0.7, 7.4, and 7.8, and so on in the LSTM case, like 0.4 and jumps to almost 0.5. So this means that this kind of things like the CNN and LSTM baselines actually they need more activities or they need more information to detect the thing. But on the other hand, on the graph CNN based approach of ours, the existence of the adjacency matrix and the representation of the graph itself was helpful to achieve this static performance across the number of nodes. In conclusion, we showed that the chronological order of activities can be used to identify unknown ones. We showed that on 2 datasets, the extrasensory dataset and the BAMAP dataset, and also the MAPAP dataset was a scripted dataset, and the model learned this bias or this script itself. So basically, it strengthened our assumption that this chronological order is indeed useful to identify unknown activities. We also showed that with at least one known activity, we can know all the preceding and all previous activities of specific user. We also showed that graph CNNs already exceed the baseline methods such as the CNN, the LSTM baselines, which suffer from the exploding error in the case of the LSTM baseline or RNN-based baselines, and also the lack of relationship between activities in case of the CNN baseline. We also showed that HAR-GCN is agnostic to the number of observed activities. So basically, it gives out a consistent performance in case of 3, 5, and even to 25 activities, unlike the CNN and the LSTM baselines. Thanks for attending this presentation. We are happy to receive your questions. Our code is open sourced on the GitHub link provided in our paper.